we plug it in the application and it works, but after just a few hours, this weakness is going to degrade quickly, and we have, for example, developing short in the gate oxide that only develops during the operation. In this part, we're going to discuss the back end, so everything that happens after the active parts of the devices have been already processed, and what happens next through cutting of the wafers, also thinning the whole wafer, and packaging and testing. And also, few additional topics that come from different directions are very important, and I wanted to put them somewhere. I call it fabrication issues, so this is also what we find here. So where we have finished, we have processed the MOSFET transistors, different devices. There can be also resistors, capacitances, even inductances, whatever we need for analog mixed signal circuits, memories, and all those blocks, metallization. And everything is made on one wafer after a huge number of process steps. Next thing is we have to make it ready for selling to the customer and putting into the product. So it has to be properly tested, it has to be packaged. And all those things are now called the backend. So first thing is, still before dicing the wafer, we have possibility to test that the individual dies that will be later separated, that they are working properly. So we're going to test the circuits by putting a needle probes one by one, as well as in this red frames. This is a so-called scribe line. This is a like peripheral part of the wafer, which is a waste part, because later a saw is going to run through it. But still, it has a value of few micrometers where we can put control devices. And these control devices, they have been important through the whole processing, because this is where how the process is being monitored. Those control devices are being measured after nearly every process step, and then we can tell, is it still everything okay? If something went wrong, then we reject the wafer and just don't spend any more effort, costs, and resources on that. So this scribe line has this function throughout the production, but in the end, also when everything is ready to put into the packaging stage, we have also this testing on the wafer, so-called wafer sort. And the dies, which they have some measurable defect, then they are being marked. Probably in the past it was like physical marking with a dot, but now it's like really everything is mapped on the wafer map, and then we know that after dicing these fall out and are not being used for packaging anymore. Next, when we know everything about that, what happens is the grinding of the wafer. So it's something similar as we had for the planarization, but here for back grinding, in fact, we don't want to thin it from the top where we have the active part, but we have this all hundreds of micrometers of substrate which we want to thin. For example, there are some packages that are really small, thin, and if we would simply cut the wafer and glue it into the package and then bond it, it would then stick out, it would not fit. So there are more and more requirements when we order chips. We have to say, what is our wish, what should it be? 15 micrometers, 100, 200, or maybe less than any of those numbers. So there are some standard values, but also there are some customer-specific values, so it's also possible to do different things depending on the application. Next, we have dicing. There are, the dicing can be done with a scriber, with a blade or laser cutter, depending, again, what in maybe the commercial applications where also we have millions of chips, then it will be done differently than somewhere elsewhere for different than silicon technologies. But basically, we have these several methods of sewing. And then we have assembly. And assembly, it can be a very big, again, topic, because we have so many sorts of packages. And with new sensor technologies and communication interfaces with photonics, the requirements on the packages are also growing. Then we have the scaling trend that on one hand we might want to have smaller package, on the other hand we might want to have system on package with many things inside. So I'm just talking here about the basics that maybe for the prototyping it might be relevant for you. If you're really going to work in the applications or packaging, then anyway you will learn much more, and then you're invited also to come and present one day here at the Institute. So we have basically two types of bonding wire, the ball bonding and wedge bonding. And what we have for most packages is that there is this substrate with a lead frame and a place to put the package. So this substrate with lead frame is the typical what we see with the deep packages that can be with 6, 8, 10, 12 pins that very often for like also maybe as if you have done some hobby electronics, then you had it many times in your hand. Similar, it's also for SOIC packages. So this lead frame provides electrical connections to the package pins, and what only we have to do is place the chip on it, bond to the respective lead frame wirings, and also what's done later is a globe top is put on top like a resin to provide environmental protection, mechanical protection, and then the package is being closed. So these two types of bond wires, very often it's flexible to use one or another, but very often also we have to be careful which one is made of gold, which one is aluminum, and respectively to be compatible, we have to ask the assembly house what they do and what kind of bond part, the top metal layer that we have on our chip, should it be aluminum or gold, because there might be some incompatibility. The difference also in the bonding is which one has a finer pitch. So the scale technologies, they will have smaller and smaller bonding pads, and also they will be closer together so that we can, for scaling also we can add much more control interface signals. And because of that, very often we need to have fine pitch, and then wedge bonding will be better. Then other than bond wires, there are also packages that use the so-called flip chip, where there is the later from outside, when we take several different packages, if they have the ball grid array, for example, at the bottom, then most likely it's a flip chip. They tend to be very thin, and unfortunately also much more difficult from the reliability point of view to realize. So what we have is this attachment balls, and there has to be alignment between the package and these deposited balls or metal pads. And then in the thermal process, it's being integrated together into a solid structure. So one more thing that is unacceptable, for example, in automotive application, is that these balls, they have very often some traces of lead, and this can cause alpha particle emissions. So they are more than likely to cause some single event effects, which for like the particle interacting with the electronics can cause transient currents, which cause soft failures or potentially even latch up. And then we have the whole family of advanced packaging. And here you can see the gradual scaling from monolithic integration, part A of the picture, through 2D integration when on the substrate of our package. Inside the package, we have 2 dies, side by side, each with bond wires. The 3D integration is when we have the through silicon via. So we have 2 dies bonded together. One of them, so what we can see in picture 3 is that only the bottom die has the bond wires and the top one is not connected. But we can imagine lots of configurations also that both of them are somehow bond wired. So it can be very individual. And this is the 3D integration. Then something that you're going to hear, read, maybe work with more and more is the 3D integration with photonics. In which case, we have the photonics to communicate with the optical fiber to the outside, which of course then needs appropriate package to enable this interface. But more and more we are talking about photonics integrated in the single package. And this is something that is going to come in the future to limit the, so to counteract the speed limits of the propagation of the charge carriers because the light can go much faster. And on the large dimension chip or package, then this kind of communication might be important. Or even within the large monolithic chip, this might also take place. And then we have so-called also 2.5 integration, where we have and the optical fibers and the integrated circuit. So what we see is that there are those different types of packages, and in terms of what we see inside, and also in terms of the package material, because sometimes we need the special requirements for certain sensor, environmental requirements to be able to, for example, transmit certain wavelengths through the package, so there will be optical opening windows, for example, for the optical sensors. So in a short overview, then certainly there is much more to discuss in this topic. And so in summary, what we see is the wire bonding, ball grid array with the, most of the time, the flip chip. And in terms of packaging, I don't have a good picture, but at least I have an added link where you can also learn about it. What we have to know is that some applications, they need large areas of silicon. And it's better to, there are different ways to consider it. You can slice it and make then packaging side by side for the large application of, for example, panel detectors. But it's also possible to do wafer level packaging, where in the single processing step, the packaging is being done, or even panel level packaging, which is like one step further from the wafer level packaging, where several wafers are handled at the same time for the packaging steps. So it's and the type of packaging and the complexity and also how we handle it to make it more parallelized process. Similar like also we were talking in the fabrication steps of the individual devices, or process like photolithography that happens step by step, or some processes like diffusion, where for the whole wafer this thermal process takes place. Then regarding the fabrication issues, so far once we have got as far as the packaging, we're almost at the end of the cycle of the production. But what has to be done is the so-called burn-in. So it could be that some parts are weak. They have some weakness, and we plug it in the application and it works. But after just a few hours, this weakness is going to degrade quickly, And we have, for example, developing short in the gate oxide that only develops during the operation. And it's enough to operate it for short time, but at increased temperature in order to replicate what would happen over several years of operation. And by doing this burn-in, that means putting the chips in the oven, operating for some hours, we can reproduce all the failures that will happen there in the fabrication process during the first several hours, and then we avoid having shipped them to the customer, and then the customer complaining that like maybe 1% of the chips that you have delivered we have returned from our customers, saying that something went wrong and it doesn't work. So, and for some critical applications, like you can imagine health applications, transportation, that's something that we definitely would have problems because the safety maybe of the operator or somebody was in danger. So the reliability is very important to consider already early on. And with this burn-in, we can increase the reliability, reduce the number of failures, and still there is certain probability of failure, but hopefully they are just some random events that are very unlikely to happen also for the time of the, as long as the product has been designed for. So this reliability is also a subject to design and how we design the lifetime until the wear out stage happens, and the number of failures is, the failure rate is increasing again. We would like to have as long as possible, but again, it's the question of budget, how much effort we put into the reliability. But generally, this so-called bust-up curve, that first it's high, then low over the lifetime, and then the wear-out stage high again, then this is the typical reliability curve. And once the chips are packaged, they have been going through burn-in. Then for the production, there are as you can guess from the wording, final production test. So that is the final step. Each device must be tested in the production. And just similarly, like it was tested with needles on the wafer level, now it's being tested in the package. So we filter out the defects that happened after burn-in. And for each chip, there is a dedicated test program which tests the functions that the chip is supposed to deliver. Each chip will have also dedicated test mode where we can access some internal parts which normally are not available in the application, but just for the test purposes. And for example, if there is some function which should generate certain current to generate slope, for example, for integration purposes, or certain time generator, time interval, these kind of things can be tested. Then one more part, which is not done for every chip, is environmental and stress testing. So in the first one, the point was to detect if there was some failure, maybe short of 2 wires, missing via, or something like that. We're supposed to detect it in the final production. In the environmental and stress test, it's also a kind of reliability overview. So we tested, for example, at extreme conditions like increased humidity, high pressure, extreme temperatures, but also normally having to complying to ESD, electrostatic discharge, radiation on mechanical stress. So this really depends on what the application is requiring. And for that, only a certain number of samples is selected. Usually it's defined by standards. For example, in JDEC standards, there are lots of standards for environmental testing. It describes how many samples have to be tested, in which way, in which operating conditions, how they are then retested to evaluate that everything is still good and if for such and such environment this chip inside a specific package can be later allowed for. So these kind of advanced technologies that we have discussed before, the 3D integration, the advanced packages, we have to keep in mind that they have also influence on this final production testing as well as environmental testing, but especially production testing and the qualifications, because we have new types of devices, new types of packages, and the JEDEC standards, the standards take years for the experts to agree what is right based on the field collected data, and very often, and the development of standards is much slower than the progress of introducing of new technologies. And very often now, what we have the situation is that some custom solutions have to be introduced, which are not defined in the standards. Customers that buy the integrated circuits, they like to have things according to standards because they know, okay, there is some regulation. If it's not standardized, then there has to be custom solutions, and with the problem that between different companies also the solution might differ quite a lot. So that's one of the things that we have to notice that also have a huge impact on the development of circuits, and hopefully not reliability, but potentially that can be also at risk. Then with the larger packages, we have large number of pins, and for the even wafer sort testing, the testing machines, they have to have much more needles, and the force per, which is specified per needle, the total force is getting one of the important things for developing new testers, not just the number of interconnections, but just this mechanical considerations. For integrated solutions, including sensors, it's not anymore electrical testing only, because there is some interaction between the electrical and, for example, temperature, pressure, optical of different wavelengths, timing. So these kind of things we want to have tested for every single chip. And so test engineers have also lots of new challenges related to that. At the same time, we want to keep the test time low, because test time is one of the main factors of how much the chip is going to cost. So another issue is the thermal budget. I have mentioned it briefly by talking about the 3D monolithic CMOS structure, where we have PMOS and NMOS at different level. But generally, that's something that we were hearing throughout the last several units about the processing, and some process steps like diffusion, ion implantation, oxidation, or epitaxy, they are at very high temperature, sometimes close to the silicon melting temperature. Then there is the metal deposition, from copper down to aluminum inside the integrated circuits. But we might have also some other, I didn't look on the temperatures of other metals that are taking part, for example, as aligners. So this is certainly, these temperatures are also playing a critical role. And that far we were talking on the processing on the wafer level. But then we have also packaging and soldering and application. And what is necessary to keep in mind, what is the, for example, temperature of the application. This temperature cannot be higher than melting of the interconnections that is done for soldering on the PCB. This one cannot be higher than what's necessary as temperature for bonding to the package, and so on. So whenever some temperature changes, and starting from the application, but maybe that different type of packaging or soldering, this will have impact on all the previous process steps, that this thermal budget has to be kept integral. So when we look on the thermal budget, just once again, we have the silicon chip that it's upside down, and the process steps thermally go from highest temperature from the bottom down to the top where we have the lowest temperature, and then the other post-backend steps are respectively at lower temperatures. So economy in IC fabrication. It's a very simple for contribution. What contributes to the production cost? Most of the time we're speaking about the chip area. And certainly that's very important to have the process scaling so that in the same chip area we can fit more function, more transistors. But there are few other topics. With the increasing integration, we have higher number of masks. With multiple patterning, single layer needs several masks. Then testing time, the time where the chip sits in the tester, even if it's just 1 or 3 seconds, that's already a lot because we have thousands, hundreds of thousands of chips to test. And finally, yield. So from the finally produced chips, if there are defects, then those reduce yield, and that's all the wasted resources that are not effective. So yield, increasing the yield, reducing the defect density, and controlling the process steps, that's also very important. So chip area, number of mask layers, testing time, and yield. So unfortunately, the yield is not 100%. And the interesting thing is that to get a yield in the range of 99%, which is, let's say, at the edge of what can be acceptable, it needs enormous precision in controlling each individual process step. So in a modern circuit, we are talking about approximately order of magnitude hundreds of process steps. Each of them is independent. And the total yield, if each process step is 0.99, 99%, within the range. And if it goes beyond this 99%, then we have certain failure. Then if we calculate 0.99 to the power of 100, that will be the total yield that we have in the end. So if that was the situation, independent processes and the direct consequence on the failure that is detectable, then we would have 37% yield having 99% at single process step. That tells us that for many process steps, it's maybe not so, it's not linear, but maybe not just as simple as that. But that tells us that there are many process steps where this control must be much higher than 99%. And so one of the things that also we have available in the design process is the variation. We have information from the process. What is the variation in parameters? As for example, for simulation, we are using the threshold voltage for PMOS, P-channel and NMOS channel transistor. And that tells us how much the transistor, what are the ranges of the threshold, which directly have impact on resistance, off-state leakage current, speed of the transition, and so on. So transconductance on currents. So there is a complex circuit where we have simulated each transistor with those possible 4 corners, so-called fast, 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 slow, 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 fast. So each 4 possibilities. We'll run simulation at each temperature. If there is some independent from different type of transistor or resistor or capacitance, an independent process step, then that adds each of those process devices adds additional corners in the process simulations. So we end up, our designer ends up in making simulations over all those corners, making sure that at each process corner, which is related to some deviation in one of those single 100 processes in the fabrication, one process is somewhere towards the right, left, top, bottom. And we have to make sure that everything, the whole complex circuit still works. And that's only covered within the corners. If any parameter goes outside of these specified boundaries, then it's not guaranteed that the circuit is still going to work properly. So something might get completely out of specification. So, of course, not all the processes are related to MOSFET transistors. There are metallizations. And also another tool is Monte Carlo simulation, which helps estimating the yield of what will be the final yield. So there is a lot of contribution to the final yield from the foundry, but also the how thorough the design is being made. And in terms of the control at the fabrication stage, there is something that we call statistical process control. Basically, it reduces to two parameters that I'm going to describe. It's about controlling each process steps and describing it by parameter so that we can monitor the stability of the process and, if necessary, improve it. So each manufacturing step is being measured doing physical measurements like oxide thickness, diameter of via, contact, channel length, those placed in the scribe line in between the chips where the sewing takes place. And also electrical monitoring. So for example, threshold voltage of MOS transistor, polysilicon resistance, effective channel length, which is also measured electrically. Once we see that the parameter of the process monitoring goes out of the spec, then also we want to monitor the temperature, pressure, and gas flow so that those, if anything went wrong, we have to analyze, is it coming from the machine or from some other environmental issues, even something like vibration, a little earthquake or vibration coming from motorway that is nearby. So this has to be also, all these parameters have to be monitored. And let's imagine an example where we monitor a diameter of a contact, so a physical measurement. And the mean should be 0.2 micrometers. The standard deviation, exactly, it varies depending on the circumstances. But for each sample, for each wafer, let's say that we measure the via, we get certain number, and we have upper and lower control limits. So the upper and lower control limit, as well as the calculated mean value and the calculated standard deviation, that so it's very much statistical process, but statistical, giving us statistical history, but then refers to each unit measurement, helps us to calculate for each process step the value of the CPK and CP parameter. So let's have a look on what they are. So CP is the limit, the distance between upper or lower limit minus the mean divided by the standard deviation and divided by 3. That's because traditionally it used to be considered that 3 is the good number for good enough yield. And we would like most of the measurements to be within this CPK limit. If it's outside, then the process is being monitored. What went wrong, that it's out of this limit, and whether we can continue the production or not. Typically, too high CPK will be shown when the mean value drifts out of range that was shown historically. And then we can tune a device in order to bring it back to the mean. If the standard deviation drifts, then we see that both CPK and CP are changing. And very often that will be, for example, machine failure, something that if we want to tune, it will likely also influence all the other process steps. So it's important to recognize it as soon as possible. This monitoring helps us capturing if there is something like a glitch, unexpected glitch from the normal situation, and then capturing out the wafers which don't fit the expected fabrication, so that we prevent it from further production, prevent it from going into packaging, and therefore increasing the yield and reliability of the product. For this lecture, one more thing that I would like to cover is the environmental footprint. This is the last topic covered in 2 slides, but very important, especially these days. We have experiencing large growth of the microelectronic industry. It's very significant scaling, and both have a very large impact on the environment and also the greenhouse emissions. So looking alone at the energy consumption, for the different clean room classes, which the class has to be improved and go to upgrades to better and better air monitoring and control, we have increased the energy consumption because the flow of air must be more accurate. There are additional filters and some other complicated things which are behind the clean room control. And what we can see that from years 2002 to over the 1 decade, we have quadrupled the power consumption per meter square, whereas the number of the clean rooms, it's also increasing. So one thing is this additional energy consumption. And second thing, it's the pure water consumption. So we need ultra pure water after many process steps to clean the wafer from any dust, any remaining compounds that are possible to clean away with the water through distilled water. And that means a very large water production, waste of water, but also energy, and maybe most of all the energy to purify this water. So regarding the environmental impact, I have added several links. It's some of these publications date from some years ago, some eye-opening articles also about the impact of the industry from last year. And the environmental responsibility of the microelectronic industry, considering how rapid growth we can see in the microelectronics, it's very slow, the process of taking responsibility. And I think it's also important to mention that, highlight that hopefully this page is going to be getting more and more significant. I haven't looked for all the resources, but nevertheless, there are some regulations and voluntary industry agreements that target introducing the life cycle assessment. So what are the environmental costs and possibility also for recycle of the different components and materials, as well as calculation of the greenhouse emissions. So we can see over the last 1, 2, 3, 4 years, so really happening now that more and more companies are doing this analysis of the greenhouse emission. And we have the regulation in the European Union and in the US that show that this will be more and more mandatory step for the microelectronic industry to report on that. And also there are associations like the European Semiconductor Semiconductor Industry Association, which gather large manufacturer microelectronic companies which agree on the targets of also reducing this, for example, PFC gases, which are also related to the climate change. So with this important accent, I would like to summarize this lecture part. So that was the last part in this course. And what you could see is the different topics of what happens after the active structures have been fabricated on the wafer. There is still a long process of the back end, preparation for packaging, the whole topics of testing, that also are influencing the reliability and yield, and finally the advanced process steps for packaging, what also enables further the 3D integration. So with that, thank you for your attention.
You're the signal in my static hum, a perfect match we've overcome. Wires cross, but we still run. Sparks fly in circuits